Hello there, and welcome to the Sleep Well channel. I'm so glad you have found your way here to this quiet corner of the world. The day is now behind you. The noise and hurry have softened into a distant hum, and all that is left is this moment here in the stillness. There is nothing you need to do now, nothing to solve, and nowhere else to be. Just allow your body to grow heavy, to feel the gentle support of the surface beneath you. Let your breathing slow, finding its own soft, easy rhythm, in and out. Imagine each breath carrying away a small piece of the day's weight, leaving you lighter, calmer, and more present in the quiet of this room. Tonight, we are not on solid ground. We are drifting, floating on the quiet, endless river of time. It is a force so familiar, we rarely notice it, a current that carries every moment of our lives from a past we remember to a future we can only imagine. But this river is not as simple as it seems. It holds deep, still pools of thought, gentle eddies of logic, and quiet questions that have puzzled philosophers and physicists for centuries. These are the paradoxes of time, but tonight we will not wrestle with them. We will not try to solve them. Instead, we will simply drift through them, one by one, letting their wonder wash over us like starlight on a calm sea. Some of what you hear may spark your curiosity, while other ideas may simply become a soft background murmur as you find your way to sleep. And just before we begin, if these quiet journeys into the heart of mystery help you find rest, consider gently liking and subscribing. It helps other sleepy souls find their way to this harbor too. But for now, let your mind go. Let the current take you. Our journey begins. We live our lives carried by a silent current, one that flows only in a single direction. This is the arrow of time. A broken glass never reassembles itself on the floor. An old tree never shrinks back into a seed. We remember yesterday, but we cannot remember tomorrow. This one-way flow feels as natural as breathing, yet it is one of the deepest mysteries in the universe. At the smallest scales, the fundamental laws of physics do not seem to care about direction. The dance of atoms, the spin of an electron, could just as easily run backward as forward. The equations are symmetrical, and yet, in our world, time never reverses. The river only ever flows downstream. Scientists often link this arrow to entropy, the universe's slow, steady march toward disorder. The cosmos began in a state of incredible order, a single hot, dense point, and has been unwinding ever since. Every star that burns, every wave that crashes, every thought that flickers in your mind is part of this grand, cosmic exhale. But this only pushes the question back. Why did the universe begin in such a perfect, ordered state to begin with? No one knows for sure. The arrow of time is not a law we have discovered, but a cosmic habit we observe. A relentless, quiet insistence that the past is fixed and the future is yet to come. As you lie here, you can feel it in the steady rhythm of your own heart. Each beat, a small, irreversible step forward, carrying you gently through the unfolding night. Now, imagine for a moment that this river of time is not a river at all. Imagine instead that time is a vast frozen landscape. This is the idea of the block universe, a theory that arises from Einstein's relativity. In this view, the past, the present, and the future are not separate. They all exist simultaneously, laid out like a single, unchanging tapestry. What we experience as the present is simply the slice of that landscape illuminated by the spotlight of our awareness. Your childhood is still there, written into the fabric of space-time. The moments of your future are there too, waiting in the quiet distance. Our sense of time's flow, that feeling of moving from one moment to the next, might be an illusion, a trick of human consciousness. The universe itself does not flow. It simply is. This idea can feel strange, even unsettling, because it suggests that the future is already written. But it can also be a source of profound peace. It means that every moment you have ever lived, every joy, every connection is not gone. It is preserved forever in the great block of space-time, as real and permanent as any star in the sky. As you rest, your awareness is simply a gentle light moving slowly across this timeless landscape, illuminating one perfect moment right here, right now. This leads us to a gentle question that has echoed through the halls of philosophy for centuries. Is only the present moment real? This is the idea of presentism. It suggests that the past is gone, a collection of memories and echoes, and the future is not yet formed, a realm of pure potential. In this view, the only thing that truly exists is the now. It is a thin, shimmering sliver of reality, constantly vanishing and being reborn in the same instant. This feels much closer to our own experience, the sense that this moment right here is all there is. The alternative called eternalism holds that all moments are equally real, echoing the block universe. It suggests that Socrates is just as real as you are, simply located at a different point in space-time. Scientists and philosophers are still divided. Physics seems to lean toward eternalism, where time is another dimension like space. But our own consciousness insists on the primacy of now. Perhaps both are true in their own way. Perhaps reality is a vast, eternal landscape, but consciousness is a traveler that can only ever experience one location at a time. The quiet space you are in right now, the soft darkness, the gentle rise and fall of your breath. This is your location. And for you, it is the only place in the universe that matters. Let's drift now into one of time's most famous thought experiments, a question so simple yet so profound, it has captured the imagination for generations. This is the grandfather paradox. Imagine you could travel back in time. You step into a machine, and with a soft hum, you find yourself in the world of your ancestors. You meet your grandfather as a young man, long before he ever met your grandmother. What if by some accident you prevented him from ever meeting her? If they never meet, your parent is never born. And if your parent is never born, then you are never born. But if you were never born, how could you have gone back in time to cause the accident in the first place? It is a perfect, gentle loop of logic that seems to have no exit. It is a whisper of a question about whether the past is a fragile, changeable thing or something solid and unyielding. Some physicists suggest a solution: parallel universes. When you go back and change the past, you simply create a new timeline, a new branch of the river where you were never born. But the timeline you came from remains untouched. You would be a visitor in a world that is no longer your own. Another idea is that the universe is self-correcting. The laws of physics might conspire to prevent you from ever succeeding. Your attempt would fail through a series of unlikely coincidences, as if time itself were gently pushing back, protecting its own history. Perhaps the river of time simply flows around the obstacle, ensuring that what has been remains. There is no need for an answer tonight. Just feel the quiet elegance of the question, a ripple in the fabric of what was, and what is, and what might be. From this paradox flows another equally strange and beautiful. It is called the bootstrap paradox, and it whispers of things that have no origin. Imagine a time traveler who is a great admirer of Shakespeare. He travels back to Elizabethan England with a book of Shakespeare's plays, hoping to meet the great playwright. But when he arrives, he discovers that Shakespeare does not exist. No one by that name has ever written a play. Desperate to ensure the plays are not lost to history, the traveler finds a publisher and has them printed under the name William Shakespeare. The plays become famous, celebrated for centuries, until one day a future time traveler picks up a copy and decides to take it back in time to meet its author. So the question is, who wrote the plays? They weren't written by Shakespeare, and they weren't written by the time traveler. They simply exist in a closed loop with no point of creation. This is the bootstrap paradox, named after the idea of pulling oneself up by one's own bootstraps. It can apply to an object, an idea, or even a piece of information. A story with no author. A melody that wrote itself. It challenges our deep-seated belief that everything must have a beginning. But in the strange logic of time, perhaps some things do not. Perhaps they are perfect, closed circles, self-sustaining echoes that exist simply because they have always existed. Like a quiet, eternal hum beneath the surface of reality, a story that is its own cause forever and ever. Let us now consider a paradox not of time travel, but of motion itself, a puzzle so ancient it was first posed by the Greeks. Imagine a race between the swift hero Achilles and a slow, steady tortoise. To be fair, the tortoise is given a head start. To win the race, Achilles must first reach the point where the tortoise began. But by the time he gets there, the tortoise has moved a little farther ahead. So Achilles must then cover that new, smaller distance. Yet again, by the time he does, the tortoise has inched forward once more. This continues forever. Each time Achilles reaches where the tortoise was, the tortoise has moved on. He is always getting closer. But he can never quite catch up because he must first cross an infinite number of ever smaller gaps. This is one of Zeno's paradoxes. It seems to prove that all motion is an illusion. Of course, we know in our world that fast runners overtake slow ones. The solution lies in mathematics and physics. An infinite series of numbers can, in fact, add up to a finite total. But the paradox still holds a quiet beauty. It reminds us that even the simplest movement, a step, a breath, a thought, can be divided into an endless cascade of smaller and smaller moments. It invites us to ponder whether reality is a smooth, continuous line or a series of tiny, indivisible steps. Perhaps each moment is a small, perfect leap across the stillness, and the flow we feel is just the gentle rhythm of those infinite jumps, carrying us from one now to the next as softly and as surely as your breath carries you now toward the edge of sleep. And so we drift from the paradox of a past that might be unchangeable to a question that unravels the very fabric of the present. We feel as though we all share a single, universal now, a moment that is the same for everyone everywhere. But Einstein's relativity whispers a different story. It suggests that now is not a constant, but a personal experience different for every observer. Imagine two people moving relative to one another. Their different motions cause them to slice through the block universe at slightly different angles. This means their definition of now across vast distances is not the same. For one, an event on a distant star might be happening now, while for the other, that same event is still in the future. This is not a trick of perception, but a consequence of the geometry of space-time. There is no single cosmic now that binds the universe together. Instead, there are infinite nows, a shimmering layered tapestry of present moments, each one valid, each one real. As you lie here perfectly still, your own now is a quiet, peaceful plane stretching out across the cosmos. It's a humbling thought that our present moment is not the universe's present moment. It is simply our own. And in this quiet darkness, your now is perfect and whole, a single, peaceful slice of eternity that belongs only to you. This idea deepens with the understanding that if two observers have different definitions of now, then events in your future might already be in someone else's past. If all these different nows are equally real, then all of time must be real. The past is not a memory, and the future is not a possibility. They are places just as real as the room you are in right now. This vision of a timeless, eternal reality can offer a profound sense of peace. It means that every moment of beauty, every shared laugh, every quiet instance of connection is not lost. It is etched permanently into the fabric of existence. The light of a long-dead star still travels through the cosmos, and in the same way, the light of a past moment is still shining somewhere in the block universe. It is a universe where nothing is truly lost, only located at a different point in the great silent map of what was, what is, and what will be. Your life is not a fleeting story that vanishes as it is told. It is an enduring landscape. And as you rest tonight, you are simply pausing in one of its quiet, beautiful valleys, surrounded by all the moments that have made you who you are. But let us drift back to our own experience, to the feeling of time passing. Here lies another more subtle paradox. We feel time's flow as a continuous stream, yet the present moment itself seems to have no duration. It is an infinitely thin line between the past and the future. By the time you become aware of it, it has already gone. How can we exist within something that has no duration? It is like living on the edge of a shadow. This paradox invites us to see the present, not as a point in time, but as a process of becoming. It is the constant unfolding of reality, the ceaseless transition from potential to memory. As you breathe in, the future becomes the present. As you breathe out, the present becomes the past. This quiet rhythm is the true nature of the now. It is not a place you can stand, but a movement you are part of. A gentle, endless wave, and you are floating upon it, carried safely from one breath to the next. This leads to a philosophical puzzle, first articulated by J.M.E. McTaggart, who argued that our concept of time is inherently contradictory. He proposed two ways of describing events: a static, unchanging order where 1900 always comes before 2000, and a dynamic series where an event changes from future to present to past. McTaggart argued that time requires both of these to be real, but that they contradict each other, leading him to conclude that time as we perceive it is an illusion. While philosophers still debate his logic, the paradox offers a gentle invitation to see time from two different perspectives. From one vantage point, your life is a fixed story with a beginning, middle, and end. From another, it is a dynamic, unfolding journey. Perhaps both are true. Perhaps you are both the character in a finished story and the author who is writing it, word by word, breath by breath. As you rest, you can feel these two perspectives merge. There is the steady, unchanging fact of your body lying here, and there is the gentle flowing river of your thoughts drifting from one idea to the next. Let us consider the future. It feels open, unwritten. Yet if the block universe is real, the future may already exist. This leads to the paradox of free will. If every moment is already laid out in space-time, how can our choices be free? This idea, known as determinism, can feel disempowering. But there is another way to see it. Perhaps our choices, our feelings, and our sense of free will are the very mechanisms by which the future is written. Perhaps the script is not imposed upon us, but is woven from the threads of our own conscious actions. Your decision to turn left instead of right is not a deviation from the path. It is the path. In this view, free will and a determined future are not in conflict. The universe does not force your choices. Your choices are what constitute the universe. As you lie here, you have made the choice to rest, and in doing so, you have helped to write a small, peaceful chapter in the great book of space-time. And as we ponder a future that may already exist, a strange thought emerges. If time travel to the past is possible, then time travel to the future should be even easier. In fact, we are all time travelers moving into the future at a rate of 1 second per second. But what if you could leap ahead? Relativity shows that by traveling at near light speeds, you could journey thousands of years into the future while aging only a little yourself. You would arrive in a world you do not know. But here lies a quiet paradox of loneliness. You could visit the future, but you could never truly return. To come back to your own time would require traveling backward, a feat that may be impossible. So, a journey to the future is a one-way trip. You would become a ghost from a forgotten era. It is a reminder that our connection to time is rooted in our shared present. We travel into the future together at the same steady pace. And there is a quiet comfort in that shared journey, a sense that we are not alone in the flow, but are all floating on the same gentle current side by side as the world turns slowly toward a new day. We drift back now from the open expanse of the future to the tangled corridors of the past, where the logic of time travel continues to weave its gentle, unsettling patterns. We have considered the bootstrap paradox, where an object has no origin, but what of the opposite? A paradox, where information is created, yet seems to vanish into nothingness. Imagine a historian who travels to the future to learn the cause of a great historical fire. In the archives of tomorrow, she finds the answer and returns to her own time to publish it. Her book becomes the definitive account, the source from which all future historians learn about the fire, the very source she consulted. So, where did the information originally come from? It exists in a closed loop. But let us change the story slightly. What if upon her return, the historian decides not to publish the book? Now the information she brought back will never be written down, and the future archives she visited will never contain it. Where did that knowledge go? It existed for a time in her mind, a memory of a future that will now never happen. This is a quiet and strange form of an information paradox. It suggests that knowledge can be uncreated, that a fact can be plucked from a timeline, leaving no trace. It is like a whisper that once heard is never spoken, fading back into the silence from which it came. It reminds us that memory and history are not always the same. History is what is written, but memory can hold worlds that never were, futures that flickered for a moment and then vanished, as soft and as fleeting as a dream you can't quite recall upon waking. Let us now explore the predestination paradox, which suggests that you cannot change the past because your journey to the past was always a part of it. Your actions are not an interference, but a fulfillment. Imagine you hear a story about a mysterious stranger who long ago saved your great-grandparents from a fire. Fascinated, you grow up, invent a time machine, and travel back to that night. But as you arrive, you see the house in flames and realize there is no mysterious stranger. It is you who must act. You run inside, save your great-grandparents, and vanish back into the future, becoming the very stranger from the stories you heard as a child. In this loop, there is no contradiction. You did not change history, you created it. Your presence in the past was not a paradox, it was a necessity. This is the predestination paradox. It paints a picture of time as a perfect, self-consistent tapestry. Every thread is exactly where it is meant to be. If you were to travel back in time, you would not be a disruptor, but a character in a story that has already been written. There is a deep and quiet peace in this idea. It suggests a universe where everything is interconnected, where every event has its purpose, and where even the strangest loops are simply the shape of a story that is already whole. As you rest here, perhaps this moment of stillness is also part of such a loop, a necessary pause that allows the rest of your story to unfold exactly as it was meant to. Let's turn to a more modern, playful paradox, one born from the mind of physicist Kip Thorne. It involves not a person, but a simple billiard ball and a wormhole. Imagine a wormhole on a billiard table, its entrance here and now, its exit a few feet away, but a few seconds in the past. You roll a billiard ball toward the entrance. If its path is just right, it will enter the wormhole, travel back in time, and emerge from the exit just in time to collide with its younger self, knocking it off course so that it never enters the wormhole in the first place. This is another version of the grandfather paradox. If the ball is knocked away, it can't enter the wormhole. But if it doesn't enter the wormhole, what caused it to be knocked away? The paradox seems to create an impossible contradiction, but physicists who have studied this problem have found a strange and elegant solution. They discovered that there is always a self-consistent path the ball can take. For example, the ball could emerge from the past and deliver just a glancing blow to its younger self, not enough to prevent it from entering the wormhole, but just enough to alter its trajectory so that it will emerge in precisely the right way to deliver that same glancing blow. The past and future of the ball would agree perfectly. The universe, it seems, has a way of avoiding paradoxes. It finds a solution, a path where the story makes sense. It suggests that the laws of physics are not just rules of motion, but rules of consistency. A quiet mathematical insistence that reality must in the end agree with itself. And now, a question that brings the grand idea of time travel into our own quiet, star-filled night. If time travel into the past is possible, then where are all the visitors from the future? This is the Fermi paradox applied to time. Enrico Fermi famously asked, "Where is everybody?" referring to the lack of evidence for extraterrestrial life. We can ask the same of time travelers. If humanity survives for thousands or even millions of years, it seems likely that we would eventually develop the technology to visit our own past. Yet we see no clear evidence of their presence. There are many gentle possibilities. Perhaps time travel to the past is simply impossible, or perhaps it is possible, but only to timelines that are not our own, branching off into parallel worlds that we can never see. Another possibility is that future civilizations have chosen not to interfere, abiding by a strict code of non-intervention, watching us from a distance like silent, invisible guardians. Or perhaps, and this is a more subtle thought, they are here, but we do not recognize them. They may be so advanced that they can move through our world without leaving a trace. Whatever the answer, the silence from the future is a paradox in itself. The night sky is quiet, and we are left here in our own time wondering if we are truly alone in the long, unfolding story of humanity. Let us explore a paradox that touches on the very nature of our identity as it persists through time. This is the paradox of the ship of Theseus. The ancient Greek hero Theseus had a ship, and over the years, as its wooden planks rotted, they were replaced one by one. Eventually, not a single original plank remained. The question is this still the ship of Theseus? If you say yes, then consider, what if someone had collected all the old discarded planks and reassembled them? Now you have two ships. Which one is the real ship of Theseus? This ancient puzzle whispers a question about our own existence. Your body is constantly replacing its cells. Your thoughts, your feelings, your memories are always changing. Are you the same person you were as a child? What is it that has persisted? The paradox does not offer an easy answer. It simply invites us to see identity, not as a fixed object, but as a continuous process, a pattern that maintains its shape even as its components change. You are not a static thing. You are a story, a song, a wave that holds its form as it moves through the ocean of time. The ship is not the wood, it is the design, and you are not the cells, you are the life that flows through them. As you rest tonight, your body is quietly rebuilding itself, yet you will wake up tomorrow as you, a perfect, gentle continuation of the person you have always been. Drifting deeper now, we leave the solid shores of logic and float into the strange, shimmering waters of relativity, where time itself becomes soft and malleable. Here, in a universe imagined by Einstein, the steady clock we take for granted begins to bend and stretch. This leads us to one of the most famous paradoxes of all, the twin paradox. Imagine two identical twins. One stays on Earth, while the other embarks on a journey to a distant star in a spaceship traveling at nearly the speed of light. According to Einstein's theory of special relativity, time for the traveling twin will pass more slowly. The faster you move through space, the slower you move through time. After what feels like a few years to the spacefaring twin, she turns her ship around and returns to Earth. But when she steps out, she finds that decades have passed for her brother. He is now an old man, while she remains young. This is not an illusion. It is a real, measurable effect. The paradox arises when we ask from the traveling twin's perspective. Wasn't it the Earth that was moving away at high speed? Shouldn't the earthbound twin be younger? The solution lies in acceleration. The twin who left had to speed up, turn around, and slow down. This change in motion breaks the symmetry and makes her the one who experiences the lesser passage of time. This thought experiment is a profound reminder that time is not absolute. It is a personal experience, a river whose speed depends on your journey. Every astronaut who has orbited the Earth has experienced this effect on a minuscule scale, returning a few microseconds younger. As you lie here still and quiet, you are moving through time at your own steady pace, in perfect synchrony with the world around you. But somewhere in the vastness of space, there may be other travelers moving on faster currents for whom our centuries pass like fleeting days. A gentle, cosmic reminder that even the beat of a single second is not the same for everyone. This bending of time is not only caused by speed, but also by gravity. Einstein's theory of general relativity tells us that massive objects warp the fabric of space-time, and the stronger the gravity, the slower time flows. This is gravitational time dilation. A clock at sea level, closer to Earth's center of gravity, will tick ever so slightly slower than a clock on a mountaintop. The difference is incredibly small, but with atomic clocks, we can measure it. It means people who live at higher altitudes age a tiny fraction faster. The satellites in our GPS systems must constantly correct for this effect. Their clocks in weaker gravity run faster. Without these corrections, GPS would fail within minutes. Now imagine this effect, taken to its extreme. Near a black hole where gravity is immense, time dilation becomes profound. To a distant observer, a clock falling toward a black hole would appear to slow down, ticking slower and slower, until at the event horizon, it would seem to freeze its final moment stretched into an eternity. For the clock itself, time would continue to pass normally, but for the outside world, it would be frozen forever at the edge of the void. This strange, silent stretching of time is not science fiction. It is a fundamental feature of our universe. It tells us that time is not a rigid ruler, but a soft, flexible ribbon, warped by the weight of stars and galaxies. As you rest, you are lying within Earth's gentle gravitational field, and time is flowing at its own familiar pace, shaped by the quiet, constant pull of the world beneath you. Let us explore a paradox of rotation that helped guide Einstein toward his theory of general relativity. This is the Ehrenfest paradox. Imagine a perfectly rigid spinning disk. According to special relativity, an object's length contracts in the direction of its motion. For the spinning disk, its circumference should contract. However, its radius, which is perpendicular to the motion, should not contract. But if the circumference shrinks while the radius stays the same, the geometry of the disk no longer makes sense. The ratio of the circumference to the diameter would no longer be pi. This paradox highlighted the limitations of special relativity. The solution is that in an accelerated frame of reference, like a spinning disk, space itself becomes curved. The geometry is no longer simple and flat. The paradox resolves itself by revealing that our intuitive understanding of shape breaks down under the strange rules of relativity. It is a reminder that even the most perfect forms, like a circle, can become mysterious when viewed through the lens of modern physics. The universe is not always built on straight lines and flat planes. It is a place of curves, warps, and gentle distortions, where even a spinning wheel can contain a quiet geometric puzzle. Let us drift back to the early 20th century. The prevailing view was that the universe was static and eternal. This idea was so deeply ingrained that when Einstein's equations of general relativity predicted a dynamic universe, he added a cosmological constant to his equations to keep it in perfect static balance. But then, in the 1920s, astronomer Edwin Hubble discovered that distant galaxies were all moving away from us. The universe was not static, it was expanding. Upon hearing this, Einstein reportedly called his cosmological constant the biggest blunder of his life. The universe had been trying to tell him it was growing, but he had been too attached to the idea of a silent, unchanging cosmos. This story is a beautiful paradox of scientific discovery. The answer was already there, hidden in the mathematics, but it took an observation of distant starlight to reveal it. A gentle reminder that sometimes our deepest assumptions are what prevent us from seeing the truth waiting quietly in front of us. And now, with an expanding universe, we can explore one of relativity's most mind-bending possibilities, closed time-like curves, or CTCs. A CTC is a path through space-time that loops back on itself, allowing an object to return to its own past. In essence, it is a time machine permitted by the laws of physics. These are not wormholes, but regions of space-time so intensely warped by gravity or motion that they fold back on themselves. Some theoretical models suggest CTCs could exist near rapidly spinning black holes. If they do exist, They would bring all the paradoxes of time travel into the real world. This has led many physicists to propose a chronology protection conjecture, the idea that some unknown law of physics must prevent CTCs from forming, keeping the past safe. The universe, in this view, protects its own history. We do not know if CTCs are real. They remain a beautiful theoretical possibility, a whisper in the equations of general relativity. But they invite us to imagine a cosmos where the river of time can bend back on itself, where a journey forward could become a journey home to a moment that has already been. A perfect, silent loop in the fabric of space-time. As we ponder these vast cosmic ideas, let us bring our awareness back to our own quiet personal experience of time. Here, in the stillness of the nighttime, is not warped by gravity or speed. It is simply flowing breath by breath. The paradoxes of relativity remind us that our experience is not the only one, but they also affirm that our experience is real and whole. Your time is your own. It is the rhythm of your heart, the pace of your thoughts, the gentle unfolding of this moment of rest. And in this moment, there are no paradoxes, no contradictions. There is only peace, a deep, quiet stillness that holds you safely as you drift ever so slowly toward the edge of sleep. We have drifted through the strange geometries of relativity, where time bends to the will of gravity and speed. Now, let us venture into an even more mysterious realm, where the solid certainties of cause and effect dissolve into a shimmering haze of probability. This is the world of quantum mechanics, and its relationship with time is perhaps the most profound paradox of all. Here we encounter the delayed choice quantum eraser experiment, a real-world experiment so baffling that it seems to reach back and alter the past. Imagine a single particle of light, a photon sent toward a screen with two slits. If we don't watch which slit it goes through, the photon behaves like a wave passing through both slits at once and creating an interference pattern, a pattern of bright and dark stripes. This tells us the photon traveled both paths. However, if we place detectors at the slits to see which path it takes, the interference pattern vanishes. The photon now behaves like a particle, choosing one path or the other. This is strange enough, but the delayed choice experiment adds a twist that seems to defy time itself. In this version, the decision to measure the photon's path is made after the photon has already passed through the slits. The information about its path is encoded in an entangled twin photon, which travels a much longer route. We can choose to either measure this twin photon to know the path of the first, or erase that information. The astonishing result is that the pattern created by the first photon depends on what we do to its twin photon later. If we measure the path information, the interference pattern disappears as if the first photon knew it was being watched, even though the watching happened in its future. If we erase the information, the pattern reappears. It is as though our choice in the present reaches back in time to change the behavior of a particle in the past. Physicists do not agree on what this truly means. Some argue it reveals a deep non-locality where time and space do not separate events as cleanly as we think. Others suggest it shows our classical intuition about past and future does not apply in the quantum world. There is no message being sent back in time, but the correlation remains a ghostly echo between a future measurement and a past event. As you rest here, this paradox invites us to imagine a reality that is far more interconnected, a universe where the past and the present might be whispering to each other in a language of probability and light. This quantum strangeness extends to quantum tunneling. In our world, if you roll a ball at a hill, it needs enough energy to get over the top. But in the quantum world, particles can tunnel through an energy barrier they don't have the energy to overcome, vanishing from one side and reappearing on the other, as if taking a shortcut through an impossible wall. Quantum tunneling is essential to how our sun works, allowing protons to fuse together. It is also the basis for certain types of modern electronics. But here is the paradox of time. Some experiments have suggested that the time it takes for a particle to tunnel can be, in some interpretations, faster than the time it would take for light to travel the same distance. This has led to speculation that tunneling might involve imaginary time or superluminal travel, seemingly violating the cosmic speed limit. Most physicists believe this is an illusion of measurement, that no information is actually sent faster than light. But the puzzle remains. It is as if the particle, for a fleeting instant, steps outside of normal space-time. It is a reminder that at the smallest scales, the world is not solid and predictable. It is a place of leaps, whispers, and impossible journeys where the firm rules of our world soften into a gentle, probabilistic haze. Let us now float into one of the most abstract ideas in physics, one that emerges when we try to apply quantum mechanics to the entire universe. This is the Wheeler-DeWitt equation. Formulated in the 1960s, it is an attempt to create a quantum theory of gravity. But when the equation is written, a strange feature appears: the variable for time is missing. The equation describes a universe that is static, timeless. It suggests that at the most fundamental level, there is no change, no flow, no past or future. This is the problem of time in cosmology. If the universe is fundamentally timeless, where does our powerful experience of time's passage come from? Some physicists believe time is not a fundamental feature of reality, but an emergent one. It may be an illusion created by the way our consciousness processes information. The Wheeler-DeWitt equation does not provide an answer. It simply presents a deep and quiet paradox. The universe, in its grandest description, may be a place where nothing ever happens. And yet, within that timeless stillness, we experience a life full of change, motion, and the gentle, constant flow of moments. Perhaps our universe is like a deep, still ocean, and what we call time is just the gentle ripple on its surface. Let us return to the strange connection of entanglement, what Einstein called spooky action at a distance. When two quantum particles become entangled, their fates are linked no matter how far apart they are. If you measure a property of one, you instantly know the corresponding property of the other, even if it is on the other side of the galaxy. The connection is instantaneous. This doesn't allow for faster-than-light communication, but it does suggest a deep, non-local connection in the fabric of reality. What does this mean for time? Some interpretations, like the Wheeler-Feynman absorber theory, propose that this connection works both forward and backward in time. In this view, a particle sends out waves into the future and also into the past. The interactions between these past and future traveling waves create the strange correlations of the quantum world. It is a universe filled with echoes, where a choice made now can be influenced by a handshake between a wave from the future and a wave from the past. This idea is not mainstream, but it is a beautiful and poetic attempt to explain some of the deepest mysteries. It paints a picture of time, not as a one-way street, but as a complex web of influences, where the present is a conversation between all that has been and all that will be. Now, let us consider a paradox that feels more like a riddle. This is the quantum Zeno effect, sometimes called the watched pot never boils effect. In the quantum world, unstable particles like radioactive atoms decay at random. But the quantum Zeno effect shows that if you continuously measure or observe the atom, you can prevent it from decaying. Each measurement resets the clock, forcing the atom back into its undecayed state. The more you look, the longer it survives. This is a real, experimentally confirmed phenomenon, but it feels deeply paradoxical. How can the simple act of looking change a physical process? It suggests that observation is not a passive act, but an active participation in reality. This idea has echoes in philosophy and spirituality. In the quantum realm, this is not a metaphor. It is a physical fact. It is a quiet and strange thought that the universe might hold its breath when it is being watched. That the gentle act of paying attention can, in the smallest corners of reality, hold time itself in a state of suspended, peaceful stillness. We have journeyed through the strange and shimmering world of quantum time, where the past and present seem to whisper to each other. Now, let us drift back into the vast cosmic theater of Einstein's universe, where the paradoxes are not of particles, but of stars and galaxies. This brings us to Olber's paradox, a question so simple yet so profound it took centuries to answer. Why is the night sky dark? If the universe is infinite, eternal, and uniformly filled with stars, then no matter where you look, your line of sight should eventually end on the surface of a star. In such a universe, the entire night sky should be as bright as the surface of the sun, a blazing uniform field of light. Yet we see a dark velvet black, punctuated by tiny points of light. This is Olber's paradox. The darkness of the night sky is a silent contradiction of the idea of a simple, infinite static universe. The solution came only when we discovered that the universe is not static and it is not eternal in its current form. The universe had a beginning, the Big Bang, about 13.8 billion years ago. This means the light from stars farther away than 13.8 billion light years has not had time to reach us. There is a horizon to what we can see. Furthermore, the universe is expanding. The light from distant galaxies is stretched on its journey, losing energy and shifting toward the red end of the spectrum. This cosmological redshift makes distant objects dimmer. So the darkness of the night sky is not a sign of emptiness. It is a sign of history and motion. It is the gentle, visible evidence of the Big Bang and the expansion of space. Every time you look up at the dark, peaceful expanse between the stars, you are seeing the shadow of creation. You are seeing the memory of a time before the stars had sent their light on its long journey, and the silent, ongoing stretching of the cosmos. The darkness is not an absence, but a story written in the quiet, empty spaces of the night. Let's now consider the nature of light itself, and a paradox at the heart of our connection to the cosmos. Everything we know about distant stars we have learned from their light, but that light is ancient. The light from the nearest star is over 4 years old. The light from the Andromeda Galaxy is 2.5 million years old. This means we are never seeing the universe as it is now. We are only ever seeing its past. We are looking at a cosmic time capsule. The stars we see in the night sky may have already burned out. The galaxies we photograph may have merged or faded away. This is the paradox of astronomical observation. Our window into the universe is also a window into its history. We can never have a real-time conversation with the cosmos. We can only receive its old letters. But this is not a limitation. It is a gift. It is what allows us to be archaeologists of time. By looking at different distances, we can see different epochs. We can watch galaxies being born, see stars in their middle age, and witness their final deaths. The sky is not a single static image. It is a layered collage of different moments in time. As you lie here, the faint light from distant stars is traveling through your window, ending a journey that began before humanity existed. You are the final destination for these ancient photons, a quiet, peaceful observer at the end of a long cosmic road. This journey of light brings us to another subtle thought. If the universe is expanding, some distant galaxies are receding from us at incredible speeds. In fact, beyond a certain distance known as the Hubble sphere, galaxies are receding from us faster than the speed of light. This does not violate relativity because it is space itself that is expanding between us and them. But it leads to a profound and lonely paradox. The light from a galaxy beyond our Hubble sphere can never reach us. It is forever trapped, carried away by the current of expanding space. This means there are vast regions of the universe we can never see, no matter how powerful our telescopes become. The observable universe is just a small, finite bubble in what may be an infinite cosmos. And as the expansion accelerates, driven by dark energy, more and more galaxies are slipping beyond that horizon, their light fading from our view forever. In the far future, our galaxy may be the only one visible. The others will have been carried away, leaving us in a vast, dark, cosmic void. It is a quiet, gentle, and slow form of isolation. A reminder that even in a universe full of light, there are boundaries to what we can know. And as time goes on, the sky will grow quieter, darker, and more lonely. Let us now return to the strange world inside a black hole. We know time slows down as you approach its event horizon. But what happens once you cross it? According to general relativity, the roles of time and space switch. Outside, you are free to move in any direction in space, but forced to move forward in time. Inside the event horizon, this is reversed. You are forced to move in one direction in space, inward toward the singularity. You cannot stop or turn back. In a sense, the direction inward becomes your future. The singularity, a point of infinite density, is not a place you can avoid. It is a moment in time that you must meet. This leads to the paradox of the black hole's interior. It is a place that exists in space, yet for anyone who enters, it is a journey that exists only in time. And it is a journey that ends What lies at the singularity is one of the greatest mysteries. Our equations break down, but for the traveler who crosses the horizon, the paradox is simpler. Their future is no longer a path of branching possibilities. It is a single, inevitable destination, a quiet, final convergence at the heart of a fallen star. This brings us to the black hole information paradox, one of the most deep puzzles in modern physics. According to quantum mechanics, information can never be truly destroyed. But what happens to the information of an object that falls into a black hole? General relativity suggests it is lost forever. But Stephen Hawking discovered that black holes slowly leak radiation, and over immense timescales, they can evaporate completely. So, if the black hole disappears, what happens to the information it swallowed? Is it destroyed, violating quantum mechanics, or does it somehow escape, encoded in the faint Hawking radiation? For decades, physicists have debated this. If information escapes, how does it get out from behind the event horizon? Some theories, like the holographic principle, suggest the information is not inside at all, but is stored on the surface of the event horizon like a two-dimensional hologram. The paradox is not yet solved. It remains a deep and quiet conflict between our two most successful theories, a reminder that even in the darkest corners of the cosmos, fundamental questions are waiting. We continue our slow, gentle spiral through the paradoxes of space-time, leaving the puzzles of our local cosmic neighborhood to drift again into the grand, sweeping implications of Einstein's universe. Let us revisit the idea that now is not universal and explore one of its most startling consequences, a paradox that challenges our very intuition about simultaneity. This is the barn and pole paradox. Imagine a runner carrying a long pole moving at a speed close to the speed of light. She runs toward a barn that has two doors, one at the front and one at the back. From the perspective of a farmer standing still beside the barn, the moving pole undergoes length contraction. It becomes shorter. In fact, if the runner's speed is just right, the shortened pole can for a fleeting instant fit entirely inside the barn. The farmer could in theory close both the front and back doors at the same time, trapping the pole inside. But now, let us switch to the runner's perspective. From her point of view, she is still, and it is the barn that is rushing toward her. This means the barn undergoes length contraction. It becomes shorter. From her perspective, the pole is its normal length and can never fit inside the shorter barn. So who is right? Can the pole fit inside the barn or not? The resolution lies in the relativity of simultaneity. The two events, the closing of the front door and the closing of the back door that are simultaneous for the farmer, are not simultaneous for the runner. From her perspective, the farmer closes the back door first. The pole continues to move through the barn, and just as its front end is about to exit, the farmer opens the back door and closes the front door. The pole is never trapped. Both observers are correct in their own frame of reference. The paradox dissolves when we let go of the idea of a single objective reality of at the same time. It is a beautiful and quiet illustration of how space-time itself shifts and rearranges depending on how you move through it. What seems like a solid logical contradiction is simply two different but equally valid points of view. A reminder that reality is not a fixed photograph, but a collection of perspectives, each one true from where it is seen. From a fast-moving pole, let us turn to a fast-spinning light. This is the paradox of a light clock on a rotating platform. A light clock is a simple, theoretical device for measuring time. It consists of two mirrors with a photon of light bouncing back and forth between them. Each time the photon completes a round trip, one tick of time has passed. Now, imagine placing this clock on a spinning merry-go-round. From the perspective of someone standing on the merry-go-round, the light is just bouncing up and down and the clock ticks at its normal rate. But from the perspective of someone standing on the ground, the photon is not just moving up and down. It is also moving in a circle with the merry-go-round. This means it has to travel a longer, diagonal path. Since the speed of light is constant, for all observers, a longer path means a longer travel time. From the ground, the spinning clock appears to be ticking more slowly. This is time dilation. But now, let's place the clock at the very center of the merry-go-round. At the center, there is no rotational speed, so the clock should tick at the same rate for both the person on the merry-go-round and the person on the ground. This seems to create a contradiction. How can time flow at different rates on different parts of the same spinning object? This puzzle, like the Ehrenfest paradox, points toward the curvature of space-time in accelerated frames. The geometry of a spinning disk is not simple and flat. Time itself flows at different rates depending on your distance from the center. It is a quiet spinning vortex of time where the edge moves more slowly through the present than the still point at its heart. Let us now imagine a paradox, not of motion, but of gravity and light. This is the paradox of a photon in a gravitational field. According to general relativity, gravity bends space-time. But it also tells us that photons, particles of light, have no mass. So, how can gravity, which is the force of attraction between masses, affect the path of a massless photon? The answer is that gravity is not a force in the traditional sense. It is a curvature of space-time. Massive objects do not pull on other objects. They warp the geometry of the universe around them. And other objects, whether they have mass or not, simply follow the straightest possible path through this curved space-time. Imagine a flat rubber sheet. A heavy ball placed in the center will create a dip. A small marble rolled across the sheet will curve its path as it passes the ball, not because the ball is pulling it, but because it is following the curve of the sheet. A photon of light does the same. It is following the gentle cosmic contours of a universe shaped by stars and galaxies. This is why gravitational lensing works. Why the light from distant galaxies can be bent around a closer galaxy cluster. The light is not being pulled. It is simply traveling on the curved highways of space-time. This shift in perspective from gravity as a force to gravity as geometry is one of the most beautiful and profound ideas in science. It is a reminder that the universe is not a stage on which things happen. It is a dynamic, flexible fabric, and its very shape guides the journey of everything within it, from the slowest planet to the fastest beam of light. Let us consider the nature of inertia. When you are in a car that suddenly accelerates, you feel a force pushing you back into your seat. This resistance to changes in motion is called inertia. But what causes it? Where does it come from? This question leads to Mach's principle, a deep and still debated idea. The physicist Ernst Mach suggested that inertia is not an intrinsic property of an object, but a result of its interaction with all the other matter in the entire universe. The feeling of being pushed back in your seat is, in this view, the collective gravitational pull of all the distant stars and galaxies resisting your attempt to change your motion relative to them. If this principle is true, it means that an object in a completely empty universe would have no inertia. It would have no resistance to acceleration. It also implies a deep and beautiful connection between the local and the global. The simple feeling of your own body's weight and momentum is tied to the existence of every star and galaxy in the cosmos. You are in a constant, silent gravitational conversation with the entire universe. While Mach's principle is not fully incorporated into modern physics and has its own paradoxes, it remains a powerful and poetic idea. It suggests that we are not isolated beings, but are deeply, fundamentally connected to the vast cosmic web of matter, and that the simplest physical sensations are echoes of that grand universal connection. From the pull of distant stars, let us turn to the strange fate of an object falling into a black hole and a paradox that pits Einstein against quantum mechanics. This is the black hole firewall paradox. According to general relativity, an observer falling into a black hole should pass through the event horizon smoothly without noticing anything unusual. This is the no drama principle. The strange effects of gravity would only become apparent as they approach the singularity. However, some quantum mechanical considerations lead to a different, more violent conclusion. Some theories suggest that the event horizon is not an empty, smooth boundary, but a firewall, a high-energy region that would instantly incinerate anything that tries to cross it. This paradox arises from the conflict between preserving information, a quantum rule, and the equivalence principle of general relativity, which requires the smooth crossing of the horizon. If the firewall exists, it violates Einstein's theory. If it doesn't exist, it seems to violate quantum mechanics. Physicists are still trying to resolve this deep and fiery contradiction. It is a quiet theoretical battle being waged at the edge of a black hole shadow. Does the universe provide a gentle passage into the void or a violent fiery end at the gate? We do not know. But the question itself is a reminder that our understanding of the universe is still incomplete, and that at the most extreme edges of reality, our most trusted laws may begin to break down into beautiful, unresolved paradoxes. We continue our slow, gentle spiral through the paradoxes of space-time, leaving the puzzles of our local cosmic neighborhood to drift again into the grand, sweeping implications of Einstein's universe. Let us revisit the idea that now is not universal and explore one of its most startling consequences, a paradox that challenges our very intuition about simultaneity. This is the barn and pole paradox. Imagine a runner carrying a long pole, moving at a speed close to the speed of light. She runs toward a barn that has two doors, one at the front and one at the back. From the perspective of a farmer standing still beside the barn, the moving pole undergoes length contraction. It becomes shorter. In fact, if the runner's speed is just right, the shortened pole can, for a fleeting instant, fit entirely inside the barn. The farmer could, in theory, close both the front and back doors at the same time, trapping the pole inside. But now, let us switch to the runner's perspective. From her point of view, she is still, and it is the barn that is rushing toward her. This means the barn undergoes length contraction. It becomes shorter. From her perspective, the pole is its normal length and can never fit inside the shorter barn. So who is right? Can the pole fit inside the barn or not? The resolution lies in the relativity of simultaneity. The two events, the closing of the front door and the closing of the back door, that are simultaneous for the farmer are not simultaneous for the runner. From her perspective, the farmer closes the back door first. The pole continues to move through the barn, and just as its front end is about to exit, the farmer opens the back door and closes the front door. The pole is never trapped. Both observers are correct in their own frame of reference. The paradox dissolves when we let go of the idea of a single objective reality of at the same time. It is a beautiful and quiet illustration of how space-time itself shifts and rearranges depending on how you move through it. What seems like a solid logical contradiction is simply two different but equally valid points of view. A reminder that reality is not a fixed photograph, but a collection of perspectives, each one true from where it is seen. From a fast-moving pole, let us turn to a fast-spinning light. This is the paradox of a light clock on a rotating platform. A light clock is a simple theoretical device for measuring time. It consists of two mirrors with a photon of light bouncing back and forth between them. Each time, the photon completes a round trip. One tick of time has passed. Now, imagine placing this clock on a spinning merry-go-round. From the perspective of someone standing on the merry-go-round, the light is just bouncing up and down, and the clock ticks at its normal rate. But from the perspective of someone standing on the ground, the photon is not just moving up and down. It is also moving in a circle with the merry-go-round. This means it has to travel a longer diagonal path. Since the speed of light is constant for all observers, a longer path means a longer travel time. From the ground, the spinning clock appears to be ticking more slowly. This is time dilation. But now, let's place the clock at the very center of the merry-go-round. At the center, there is no rotational speed. So the clock should tick at the same rate for both the person on the merry-go-round and the person on the ground. This seems to create a contradiction. How can time flow at different rates on different parts of the same spinning object? This puzzle, like the Ehrenfest paradox, points toward the curvature of space-time in accelerated frames. The geometry of a spinning disk is not simple and flat. Time itself flows at different rates depending on your distance from the center. It is a quiet spinning vortex of time where the edge moves more slowly through the present than the still point at its heart. Let us now imagine a paradox, not of motion, but of gravity and light. This is the paradox of a photon in a gravitational field. According to general relativity, gravity bends space-time, but it also tells us that photons, particles of light, have no mass. So how can gravity, which is the force of attraction between masses, affect the path of a massless photon? The answer is that gravity is not a force in the traditional sense. It is a curvature of space-time. Massive objects do not pull on other objects. They warp the geometry of the universe around them. And other objects, whether they have mass or not, simply follow the straightest possible path through this curved space-time. Imagine a flat rubber sheet. A heavy ball placed in the center will create a dip. A small marble rolled across the sheet will curve its path as it passes the ball, not because the ball is pulling it, but because it is following the curve of the sheet. A photon of light does the same. It is following the gentle cosmic contours of a universe shaped by stars and galaxies. This is why gravitational lensing works. Why the light from distant galaxies can be bent around a closer galaxy cluster. The light is not being pulled. It is simply traveling on the curved highways of space-time. This shift in perspective from gravity as a force to gravity as geometry is one of the most beautiful and profound ideas in science. It is a reminder that the universe is not a stage on which things happen. It is a dynamic, flexible fabric, and its very shape guides the journey of everything within it, from the slowest planet to the fastest beam of light. Let us consider the nature of inertia. When you are in a car that suddenly accelerates, you feel a force pushing you back into your seat. This resistance to changes in motion is called inertia. But what causes it? Where does it come from? This question leads to Mach's principle, a deep and still debated idea. The physicist Ernst Mach suggested that inertia is not an intrinsic property of an object, but a result of its interaction with all the other matter in the entire universe. The feeling of being pushed back in your seat is, in this view, the collective gravitational pull of all the distant stars and galaxies resisting your attempt to change your motion relative to them. If this principle is true, it means that an object in a completely empty universe would have no inertia. It would have no resistance to acceleration. It also implies a deep and beautiful connection between the local and the global. The simple feeling of your own body's weight and momentum is tied to the existence of every star and galaxy in the cosmos. You are in a constant silent gravitational conversation with the entire universe. While Mach's principle is not fully incorporated into modern physics and has its own paradoxes, it remains a powerful and poetic idea. It suggests that we are not isolated beings, but are deeply fundamentally connected to the vast cosmic web of matter, and that the simplest physical sensations are echoes of that grand universal connection. From the pull of distant stars, let us turn to the strange fate of an object falling into a black hole and a paradox that pits Einstein against quantum mechanics. This is the black hole firewall paradox. According to general relativity, an observer falling into a black hole should pass through the event horizon smoothly without noticing anything unusual. This is the no-drama principle. The strange effects of gravity would only become apparent as they approach the singularity. However, some quantum mechanical considerations lead to a different, more violent conclusion. Some theories suggest that the event horizon is not an empty, smooth boundary, but a firewall, a high-energy region that would instantly incinerate anything that tries to cross it. This paradox arises from the conflict between preserving information, a quantum rule, and the equivalence principle of general relativity, which requires the smooth crossing of the horizon. If the firewall exists, it violates Einstein's theory. If it doesn't exist, it seems to violate quantum mechanics. Physicists are still trying to resolve this deep and fiery contradiction. It is a quiet, theoretical battle being waged at the edge of a black hole's shadow. Does the universe provide a gentle passage into the void, or a violent, fiery end at the gate we do not know? But the question itself is a reminder that our understanding of the universe is still incomplete, and that at the most extreme edges of reality, our most trusted laws may begin to break down into beautiful, unresolved paradoxes. We have navigated the grand, curving landscapes of relativity. Now, our journey takes us back into the soft, uncertain mists of the quantum realm, where time behaves less like a river and more like a collection of whispers and echoes. Here, the solid line between past, present, and future seems to dissolve, leaving behind correlations that are as beautiful as they are baffling. Let us drift deeper into the implications of the delayed choice quantum eraser experiment and a related thought experiment known as Wheeler's cosmic interferometer. John Wheeler asked us to consider light from a distant quasar billions of light years away. This light travels across the cosmos and on its way passes a massive galaxy cluster. The gravity of this cluster acts as a lens bending the light so it can reach us by two different paths. Here on Earth, we can set up an experiment. We can either detect which path the light took, or we can combine the light from both paths to see if they create an interference pattern. Just like in the double-slit experiment, if we know the path, there is no interference. If we don't, there is. But here's the cosmic paradox. The light began its journey billions of years ago. The choice of which path it would take was seemingly determined back then. Yet our choice of which experiment to perform happens now. Our decision in the present seems to determine the nature of an event that happened in the distant past. Did the photon know billions of years ago that we would one day be here? Wheeler famously said, "The past has no existence except as it is recorded in the present." This experiment suggests that the act of observation is what brings the past into being. The past is not a fixed, solid thing. It is a shimmering, probabilistic reality, waiting for a conscious observer in the future to give it a definite shape. It is a profound and gentle thought that our awareness today might be sending quiet ripples backward through the ocean of time. Let us now consider a paradox of quantum identity and time. This is the Gibbs paradox. In classical thermodynamics, if you mix two different gases, the entropy or disorder of the system increases. This is an irreversible process. But what if the gases are identical? In classical physics, you could imagine tagging each atom and watching them mix. The entropy should still increase. However, in quantum mechanics, identical particles are truly fundamentally indistinguishable. If you swap two identical particles, the universe is exactly the same. This means that when you mix two identical gases, the entropy does not increase. Nothing has really changed. The paradox lies in the transition between distinguishable and indistinguishable. How can the simple fact of being identical prevent the arrow of time, as represented by entropy, from moving forward? The solution lies in the heart of quantum statistics, but the implication is beautiful. It suggests that identity and time are deeply intertwined. For unique things, time brings change. But for things that are fundamentally identical, time's arrow seems to lose some of its power. A quiet microscopic hint that in a state of perfect sameness, there is a kind of timelessness. Let us drift into a speculative but deeply intriguing idea that connects the beginning and the end of time. This is the conformal cyclic cosmology, a theory proposed by physicist Roger Penrose. This model suggests the universe goes through infinite cycles, or aeons. Each aeon begins with a Big Bang and ends with a cold, empty, infinitely expanding state. But here is the beautiful, paradoxical twist. Penrose argues that in the very far future, when the universe is empty of almost all matter and filled only with massless photons, the concepts of time and distance lose their meaning. A universe without mass has no scale. In this state, the infinitely large future becomes mathematically equivalent to the infinitely hot and dense state of a Big Bang. So the end of one eon seamlessly becomes the beginning of the next. The universe does not bounce, but rather transforms. The cold, empty death of one universe becomes the fiery birth of another. Penrose even suggests we might be able to see faint traces of the previous eon Hawking points, which are the remnants of evaporated black holes from the last cycle imprinted on our cosmic microwave background. The idea is still being debated, but it is a stunning vision. It suggests a universe that is both mortal and immortal, constantly dying and being reborn. A cosmic phoenix, rising from its own ashes over and over in a silent, endless, and beautiful cycle. Now, let us consider a paradox that touches on the very nature of existence and nothingness. This is the quantum fluctuation paradox. According to quantum field theory, the vacuum of empty space is not truly empty. It is a sea of potential where virtual particles are constantly popping into existence and then annihilating each other. This is the universe's background hum. The paradox is this: why is there something instead of nothing? Some physicists have proposed that the universe itself could have arisen from such a quantum fluctuation, that nothing, in the quantum sense, is inherently unstable. In this view, the state of absolute nothingness, no space, no time, no laws, is a fragile one. The laws of quantum mechanics could allow for a universe to spontaneously fluctuate into existence. This universe would appear from nothing, and its total energy would be zero, with the positive energy of matter balanced by the negative energy of gravity. This does not fully answer why the laws of quantum mechanics exist, but it offers a scientific framework for a question once reserved for philosophy. It suggests that the existence of our universe is not a grand miracle, but perhaps a natural, even inevitable consequence of the strange and beautiful rules that govern reality at its deepest level. Our cosmos may be nothing more than a gentle, long-lived ripple in the ocean of nothingness. Let us explore a thought experiment that blurs the line between observer and history. This is the quantum suicide in immortality. Thought experiment, a variation on Schrödinger's cat. Imagine you are in a room with a quantum device, a gun connected to a particle. Each second, the spin of the particle is measured. If the spin is up, the gun does nothing. If down, the gun fires, and you are instantly killed. The probability is 50-50. From an outside observer's perspective, after a few seconds, they will likely open the door and find you gone. But what is the experience from your perspective? The many worlds interpretation suggests that with each measurement, the universe splits into two branches. In one, you survive. In the other, you perish. The key is that you can only ever experience the timeline in which you survive. So, from your point of view, every time the measurement is made, the spin will be up. You will hear the click of the device second after second, and you will live. You will become convinced you are immortal. This is not a logical paradox, but a profound paradox of perspective. It suggests that our conscious experience is always filtered through the lens of survival. We can only witness the paths where we continue to exist. It is a strange and unsettling thought, but it also carries a quiet beauty. It implies that from your own subjective point of view, the story of your consciousness can never have an ending that you are aware of. It is a story that for its own narrator must always continue. We have floated through the strange, non-local whispers of quantum time. Now, our journey carries us back to the personal, to the way the human mind experiences and constructs its own sense of time. Here, the paradoxes are of perception, memory, and consciousness itself. They are the gentle internal riddles that shape our every moment. Let us begin with a question that touches every one of us. Why does time seem to speed up as we get older? A summer in childhood felt like an eternity. A year in adulthood can feel like it passes in a blink. This is the paradox of perceptual time. One theory is the ratio theory. When you are 5, 1 year is 20% of your entire life. When you are 51 years is only 2%. It is a much smaller relative slice of time, so it feels as though it passes more quickly. Another more beautiful idea is that our perception of time is related to the amount of new information we are processing. For a child, almost everything is new. The brain is working hard to encode these novel experiences, and this dense recording of information stretches out our subjective sense of time. As we grow older, life becomes more routine. The brain, in its efficiency, no longer needs to record every detail. With less new information, the days and years seem to blur and contract. This suggests a quiet, beautiful way to slow down time, seek out novelty, learn a new skill, visit a new place. By filling your life with new experiences, you are giving your brain more to record. And in doing so, you are stretching the fabric of your own personal time. From the speed of our lives, let us turn to the substance of our past. Our memories feel like a direct window into what has been. But here lies the paradox of memory. Memory is not a recording, it is a reconstruction. Every time you recall a past event, your brain is not replaying a video. It is actively rebuilding the memory from fragments stored across different neural networks. And with each reconstruction, the memory can be subtly changed, colored by your current mood, or blended with other memories. This is why we can develop false memories, vivid recollections of things that never happened. This malleability can feel unsettling. It suggests our past is not as solid as we believe, but it is also an adaptive process. It allows us to integrate new experiences, to learn, and to find new meaning in old events. Your past is not a static museum. It is a living, breathing story that you are constantly retelling to yourself. As you rest tonight, your brain is quietly sifting through the memories of the day, weaving them into the ever-evolving tapestry of your life. Let us now consider a paradox of consciousness and sleep. This is the Sleeping Beauty problem, a thought experiment in probability. Imagine a volunteer. Sleeping Beauty is put to sleep on Sunday. A fair coin is tossed. If heads, she will be woken up once on Monday. If tails, she will be woken up twice, once on Monday and again on Tuesday. After each waking, she is given a memory-erasing drug, so she cannot remember previous awakenings. Whenever she wakes up, she has no idea if it is Monday or Tuesday or how the coin landed. The question is, when she wakes up, what should her degree of belief be that the coin landed on heads? There are two main schools of thought. The halfers argue that the probability is still 1/2. The coin toss was fair, and she knows this. The outcome is independent of how many times she's woken up. The thirders, however, argue the probability is 1/30. They reason that over many repetitions, there will be on average 1 heads waking for every 2 tails wakings. So from the perspective of a single amnesiac, waking it is twice as likely to be a tails waking. This puzzle has no agreed upon answer. It pits our understanding of probability against our intuition about first-person experience. It is a gentle, abstract riddle that asks, how do we count our own moments of awareness? A quiet reminder that even our own consciousness can be a variable in the strange mathematics of reality. Let us drift now to the very end of time, to the ultimate fate of the universe. Here, we find a paradox of heat and cold. This is the paradox of the heat death of the universe. The second law of thermodynamics tells us that entropy or disorder in a closed system always increases. Over immense timescales, the universe is expected to evolve toward a state of maximum entropy, a state of perfect thermal equilibrium. In this far future, all the stars will have burned out. All black holes will have evaporated. All matter will have decayed into a thin, uniform soup of particles. In this state, there will be no temperature differences, no flow of energy, no change. Nothing will happen ever again. This is the heat death, a cold, silent, and eternal stillness. The paradox is this: if the universe is destined for this state, then why did it begin in a state of such incredible low entropy ordure? The Big Bang was a moment of perfect, concentrated energy. Why was the universe wound up so perfectly at the beginning, only to slowly unwind for eternity? This returns us to the mystery of the arrow of time. The universe's journey from order to disorder gives time its direction. The origin of that order remains the deepest puzzle. The idea of a final, eternal stillness can feel bleak. But there is also a quiet grandeur to it. It is the image of a universe that has given all its energy, told all its stories, and finally come to a state of perfect, unshakable peace. A final, gentle exhalation into an endless night. But this is not the only possible end. Another more violent fate is the Big Rip. This scenario depends on the nature of dark energy. If dark energy is a phantom energy that grows stronger over time, the expansion will become so powerful that it will overcome forces. In the final moments, this runaway expansion would first pull galaxies apart, then solar systems. Stars and planets would be torn to shreds, and in the very last fraction of a second, the expansion would become so strong that it would overcome the forces holding atoms together. The fabric of matter would be ripped apart. The universe would dissolve into a sea of fundamental particles flying apart so fast they could never interact again. The paradox of the Big Rip is one of finality. It is not a slow fade, but a sudden total dissolution. A strange thought that the same dark energy that now causes the gentle acceleration of distant galaxies could one day become a force of ultimate destruction. It is a reminder that the fate of the cosmos hangs in a delicate balance dependent on a force we do not yet understand. But like the heat death, this is a fate that lies in a future so distant it is almost beyond imagination. For now, the universe is calm, stable, and held together by gentle, steady forces. And we are here in a quiet, peaceful moment, floating safely in the long, tranquil afternoon of cosmic history. Our journey now carries us deeper into the subtle paradoxes woven into our own being, into our bodies, our minds, and our very sense of self as it persists through time. We have touched on the ship of Theseus, but let us delve deeper into its implications for the human soul. The paradox asks if an object that has had all its components replaced remains the same object. For our bodies, with their constantly turning over cells, the answer seems to be yes. But what of our minds? Here lies the paradox of the evolving self. Your personality, your beliefs, your desires all change over time. The person you were 10 years ago held different opinions, dreamed different dreams. Are you still the same person? If you could meet your younger self, you might feel like a stranger. This leads to a quiet, profound question. What is the thread that connects the different versions of you across time? Some philosophers argue it is memory, the chain of recollections linking your present self to your past. Others suggest it is the continuity of consciousness itself, the uninterrupted stream of awareness. Perhaps there is no single thread. Perhaps you are not a static entity, but a process, a pattern that is constantly remaking itself. Like a river, the water is always changing, but the river maintains its identity. You are both the same and different, a being of perfect continuity and constant change. This is not a contradiction to be solved, but a beautiful truth to be held. As you rest here tonight, you are not the same person you were this morning. The experiences of the day have subtly reshaped you. You are a living work of art, always complete, yet never finished. Let us now consider a paradox of potential and inaction. This is the story of Buridan's ass. A donkey stands perfectly equidistant between two identical bales of hay. The donkey is hungry, but it is also a perfectly rational creature. Since both bales are identical and equally far away, there is no logical reason to choose one over the other. Unable to make a decision, the donkey stands frozen in place and eventually starves. This ancient philosophical puzzle is a paradox of choice and symmetry. It explores what happens when there is no determining factor to break a tie. In the context of time, it whispers a question about the nature of the future. If the future is a set of branching paths, what allows us to choose one path when multiple seem equally good or equally bad? The paradox of Buridan's ass suggests that pure reason can sometimes lead to paralysis. What moves us forward is often not logic, but something else. A random impulse, a subtle unconscious bias, a gentle nudge from our emotions. It is a reminder that living in time requires more than just calculation. It requires a willingness to step into the unknown to make a choice, even when there is no perfect reason. It is a quiet celebration of the non-rational, the intuitive, the simple act of moving forward, not because it is logical, but because stillness is not an option for the living. Let us drift into a modern paradox, one born from our digital age. This is the paradox of the digital self. We now have the ability to create vast detailed archives of our lives, social media profiles, photos, journals. In the future, it may be possible for AI to learn from this data and create a simulation of you, one that can talk like you and think like you even after you are gone. Here is the paradox. Would this digital being be you? It would have your memories, your personality patterns. It could offer comfort to your loved ones. But would it have your consciousness, your subjective, first-person experience of being? This is a modern version of the ship of Theseus. If you replace the biological hardware with digital hardware, is the self still there? Most neuroscientists would say no, that consciousness is tied to the biological processes of the brain. But the question lingers. It forces us to ask what we truly value about our identity. Is it our pattern, our story, or is it the silent, ineffable feeling of being the quiet light of awareness that is experiencing these words right now? This digital paradox is a gentle, futuristic mirror reflecting back at us the ancient, unresolved mystery of what it truly means to be a self. From the future, let us return to the deepest past, to the very origin of life, and a paradox of time and information. This is the information paradox of life's origin. For life to begin, it needed complex molecules like DNA that could store information and replicate. But the machinery required to build and replicate these molecules is itself incredibly complex and is encoded in the very information they carry. It is a classic chicken and egg problem. You need the blueprint DNA to build the machinery proteins, but you need the machinery to read and copy the blueprint. So which came first? This paradox of origins has led to many beautiful theories. The RNA world hypothesis suggests that an earlier, simpler life was based on RNA alone, which can both store information and act as a simple enzyme. This would make it both the chicken and the egg. Other theories propose that life began not with a single molecule, but with a self-sustaining network of chemical reactions. We do not yet know the answer. But the paradox itself is a quiet reminder of the incredible hurdle life had to overcome. It was not a simple step, but a dance of information and function, a loop that had to somehow close upon itself to spark the first living flame. A moment of perfect, self-referential creation at the dawn of biological time. Let us now consider a paradox of perspective that touches on our place in cosmic history. This is the doomsday argument. It is a probabilistic argument that suggests we may be closer to the end of human history than we think. The argument goes like this. Assume that you are a random observer, born at a random point in the entire history of the human race. It is statistically more likely that you would be born somewhere in the middle of that history rather than at the very beginning or the very end. If humanity were to survive for millions of years and colonize the stars, the total number of humans who will ever live would be immense. If that were the case, your position would make you one of the very earliest humans, a statistical improbability. The argument concludes that it is statistically more likely that the total number of humans is much smaller, which would imply humanity does not have a long future. This argument is highly controversial, and many philosophers have pointed out its flaws. But it is a fascinating paradox of self-location in time. It uses our own existence as data to predict the future. It is a strange, unsettling whisper from the cold logic of statistics. But it is only a thought experiment, not a prophecy. The future remains unwritten, shaped not by probability, but by the choices we make, moment by moment, day by day. Our journey now carries us deeper into the subtle quantum nature of reality, where the firm ground of classical intuition gives way to a world of shimmering probabilities. Here, time is not a simple forward-moving arrow, but a complex, interwoven fabric where past and future can seem to touch in the most delicate ways. Let us consider the implications of a universe built on these quantum rules. This brings us to the paradox of quantum determinism. At its heart, quantum mechanics is probabilistic. We can never know with certainty the exact position and momentum of a particle at the same time. This inherent randomness led many to believe that the universe is fundamentally indeterministic. However, the core equation of quantum mechanics, the Schrödinger equation, is perfectly deterministic. If you know the quantum state of a system, at one moment, the equation can tell you exactly what its quantum state will be at any moment in the future. Herein lies the paradox. The underlying law is deterministic, but the outcomes we observe are probabilistic. How can a deterministic process produce random results? This is the measurement problem, one of the deepest puzzles in physics. When we measure a quantum system, its probabilistic wave function seems to collapse into a single definite state. But what constitutes a measurement? The many worlds interpretation resolves this by suggesting there is no collapse. The universe simply splits, with every possible outcome occurring in a separate parallel world. In this view, the universe is perfectly deterministic. We just only experience one of its many branching paths. As you lie here, your body is a collection of trillions of quantum particles evolving according to deterministic laws. Yet your thoughts feel free. You are a living paradox, a being of perfect, underlying order, experiencing a world of beautiful, uncertain possibility. From the nature of measurement, let us turn to the nature of creation itself. This is the ex nihilo paradox, the puzzle of how something can come from nothing. If the universe, including time itself, began with the Big Bang, then what caused it? The concept of a cause requires time. A cause must precede its effect. But if there was no before the Big Bang, then the very idea of a cause breaks down. The universe cannot have a cause in the traditional sense because there was no time for a cause to exist in. This is a profound logical and temporal paradox. It suggests the universe may be its own cause, or an uncaused event. Some cosmological models, like the Hartley-Hawking state, propose a universe with no beginning in time. In this model, as you go back toward the Big Bang, time itself gradually transforms into a dimension of space. The universe has a starting point in size, but not in time. It has no boundary. It simply is. This idea is as beautiful as it is abstract. It removes the paradox of a first cause by dissolving the very concept of a first moment. It paints a picture of a self-contained universe, a perfect four-dimensional jewel that does not need a before to explain its existence. A quiet mathematical whisper that the ultimate origin may not be an event in time, but the timeless structure of reality itself. Let us now explore a paradox that brings together entanglement and black holes. This is the AMPS paradox, or the firewall paradox. It begins with the black hole information paradox. Information cannot be destroyed, but black holes seem to destroy it. A potential solution is that the information escapes encoded in Hawking radiation. For this to work, a particle of Hawking radiation must be entangled with its partner particle that fell into the black hole. But for the black hole's event horizon to be smooth, as relativity predicts, that same particle falling in must also be entangled with the rest of the black hole's interior. Here is the quantum paradox. A principle known as the monogamy of entanglement states that a quantum particle can only be fully entangled with one other particle at a time. To resolve this, something must give. The AMPS paradox proposes that what gives is the smooth space at the event horizon. To preserve entanglement with the outgoing radiation, the entanglement with the interior must be broken. This breaking would release immense energy, creating a firewall that would destroy anything crossing the horizon. This creates a paradox of experience. For a distant observer, information is preserved. For a falling observer, space-time is violently torn apart. This puzzle remains at the forefront of theoretical physics. A quiet, intense battle between our understanding of gravity, quantum mechanics, and the nature of information and time at the edge of forever. Let's drift to a more philosophical question about the nature of a timeless law. This is the paradox of the laws of physics themselves. The laws of physics are expressed as mathematical equations that are timeless. They exist outside of time. They describe how the universe evolves, but they themselves do not evolve. But how can a timeless law govern a universe that is so fundamentally temporal? How does something that is outside of time reach in and guide the flow of events within time? This is a deep metaphysical paradox. It is the relationship between the eternal and the ephemeral. Some physicists have proposed that the laws of nature are not timeless at all. Perhaps they are more like habits, patterns the universe has fallen into over time. In the early universe, the laws may have been different, and as the universe cooled, the laws we know today crystallized into their current form. This idea, known as evolving laws, is speculative, but it offers a beautiful alternative to rigid eternal laws. It suggests a universe that is not just a machine executing a pre-written program, but a living, evolving entity whose very rules of behavior can change and grow. a universe that is learning to be itself. Now, let us consider a paradox of time and knowledge that is more personal. This is the paradox of nostalgia. Nostalgia is a bittersweet emotion, a longing for a past we remember with a warm golden glow. But here is the paradox. The past we are nostalgic for often never existed in the way we remember it. Our memory is a filter. It tends to soften difficult moments and amplify moments of joy. We create a beautiful, idealized version of the past, a story more emotionally true than factually accurate. So when we feel nostalgia, are we longing for a real place and time, or for a story we have told ourselves? Perhaps both. Nostalgia is a quiet internal process of meaning-making. It is the mind's way of finding beauty and safety in its own history. A gentle form of self-soothing. As you lie here, perhaps a gentle memory from your own past drifts into your mind. You don't need to question its accuracy. Just allow yourself to feel its warmth. It is your story, and it is beautiful. Let us end this part of our journey with a quiet paradox of the night sky itself. Every star you see is a window into the past, but the sky is also a window into different pasts all at once. The light from the moon is a second old. The light from the sun is 8 minutes old. The light from Alpha Centauri is 4 years old. The light from the Andromeda Galaxy is 2.5 million years old. When you look at the night sky, you are not seeing a single moment in time. You are seeing a collage of countless different moments, a deep layered history of the cosmos, all presented to you as a single peaceful now. The sky is a time machine that allows you to see everything at once. The ancient and the recent all hanging together in a silent, shimmering tapestry. It is the ultimate block universe made visible. As you close your eyes, you can imagine this deep, layered time. The quiet, ancient light from distant stars still traveling, and you hear now a peaceful observer at the end of its long journey. A single point of consciousness holding billions of years of cosmic history in a single quiet gaze. Our gentle voyage is nearing its end. We have explored grand cosmic theaters, and now we return to the most intimate paradoxes, those woven into our own being, our bodies, our minds, and our sense of self as it persists through time. We have touched on the ship of Theseus, but let us delve deeper into its implications for the human soul. The paradox asks if an object, with all its components replaced, remains the same object. For our bodies, the answer seems to be yes. But what of our minds? Here lies the paradox of the evolving self. Your personality, your beliefs, your desires all change. The person you were 10 years ago held different opinions. Are you still the same person? If you could meet your younger self, you might feel like a stranger. This leads to a quiet, profound question. What is the thread that connects the different versions of you across time? Some philosophers argue it is memory. Others suggest it is the continuity of consciousness itself. Perhaps there is no single thread. Perhaps you are not a static entity, but a process, a pattern constantly remaking itself. Like a river, The water is always changing, but the river maintains its identity. You are both the same and different, a being of perfect continuity and constant change. This is not a contradiction, but a beautiful truth. As you rest here tonight, you are not the same person you were this morning. The day's experiences have subtly reshaped you, and you are not the same person you will be tomorrow. The quiet restoration of sleep will remake you once more. You are a living work of art, always complete yet never finished. Let us now consider a paradox of time and potential. This is the story of Buridan's ass. A donkey stands perfectly equidistant between two identical bales of hay. The donkey is hungry, but also perfectly rational. Since both bales are identical, there is no logical reason to choose one over the other. Unable to make a decision, the donkey stands frozen and eventually starves. This ancient philosophical puzzle is a paradox of choice and symmetry. In the context of time, it whispers a question about the future. If the future is a set of branching paths, what allows us to choose one path when multiple seem equally good? The paradox of Buridan's ass suggests that pure reason can lead to paralysis. What moves us forward is often not logic, but something else. A random impulse, a subtle, unconscious bias, a gentle nudge from our emotions. It is a reminder that living in time requires more than just calculation. It requires a willingness to step into the unknown, to make a choice, even when there is no perfect reason. It is a quiet celebration of the non-rational, the intuitive, the simple act of moving forward. Not because it is logical, but because stillness is not an option for the living. Let us drift into a modern paradox born from our digital age. This is the paradox of the digital self. We now create vast, detailed archives of our lives, social media photos, emails. In the future, AI may learn from this data and create a simulation of you, one that can talk and think like you, even after you are gone. Here is the paradox. Would this digital being be you? It would have your memories, your personality patterns. It could offer comfort to your loved ones. But would it have your consciousness, your subjective first-person experience? This is a modern version of the ship of Theseus. If you replace biological hardware with digital hardware, is the self still there? Most neuroscientists would say no, that consciousness is tied to the biological processes of the brain. But the question lingers. It forces us to ask what we truly value about our identity. Is it our pattern, our story? Or is it the silent, ineffable feeling of being the quiet light of awareness, experiencing these words right now? This digital paradox is a gentle, futuristic mirror reflecting back at us the ancient unresolved mystery of what it truly means to be a self. From the future, let us return to the deepest past, to the very origin of life, and a paradox of time and information. This is the information paradox of life's origin. For life to begin, it needed complex molecules like DNA that could store information and replicate. But the machinery required to build and replicate these molecules is itself incredibly complex. and is encoded in the very information they carry. It is a classic chicken and egg problem. You need the blueprint DNA to build the machinery proteins, but you need the machinery to read and copy the blueprint. So which came first? This paradox has led to many beautiful theories. The RNA world hypothesis suggests that an earlier, simpler life was based on RNA alone, which can both store information and act as a simple enzyme. This would make it both chicken and egg. Other theories propose a metabolism-first approach, where life began as a self-sustaining network of chemical reactions. We do not yet know the answer, but the paradox is a quiet reminder of the incredible hurdle life had to overcome. It was not a simple step, but a dance of information and function, a loop that had to somehow close upon itself to spark the first living flame. A moment of perfect self-referential creation at the dawn of biological time. Let us now consider a paradox of perspective that touches on our place in cosmic history. This is the doomsday argument, a probabilistic argument suggesting we may be closer to the end of human history than we think. The argument goes like this: assume you are a random observer born at a random point in the entire history of the human race. It is statistically more likely you would be born somewhere in the middle of that history. If humanity were to survive for millions of years and colonize the stars, the total number of humans who will ever live would be immense. If that were the case, your position would make you one of the very earliest humans a statistical improbability. The argument concludes that it is statistically more likely that the total number of humans is much smaller, implying humanity does not have a long future. This argument is highly controversial, and many philosophers have pointed out its flaws, but it is a fascinating paradox of self-location in time. It uses our own existence as data to predict the future. It is a strange, unsettling whisper from the cold logic of statistics, but it is only a thought experiment, not a prophecy. The future remains unwritten, shaped not by probability, but by the choices we make, moment by moment, day by day. As our journey nears its final quiet destination, let us drift through some of the last, most subtle paradoxes time has to offer. These are not grand cosmic puzzles, but gentle internal questions that touch on the very texture of our lived experience, the way our minds and cultures have learned to dance with the ceaseless flow of moments. Let us begin with a paradox of human connection, one that spans generations. This is the paradox of intergenerational empathy. We feel a natural empathy for those who live alongside us. We also feel a connection to our ancestors. But it is often much harder to feel a real emotional connection to the people who will live in the distant future. They are abstract, faceless beings. We can know intellectually that our actions today will profoundly affect their world. Yet, it can be difficult to feel the same urgent empathy for them as we do for our contemporaries. This is the paradox. We are part of a long, unbroken chain of humanity, yet our emotional awareness seems tethered to the present. Time creates a kind of empathetic distance. This is not a moral failing, but a feature of how our minds evolved, tuned to the immediate needs of our small, local tribes. But as we have become a global civilization, this temporal myopia has become one of our greatest challenges. The paradox invites a quiet, gentle expansion of our hearts. It asks us to try to imagine those future faces, to feel a sense of responsibility, not just for the world we inherited, but for the world we will leave behind. It is an invitation to extend our empathy, not just across space, but across time. From the future of humanity, let us turn to the future of a single thought. This is the paradox of the unspoken thought. Imagine you have a thought, a fleeting idea, an image, but you never speak it, never write it down, never act on it. It exists for a moment only in the silent private theater of your own mind, and then it is gone. Did it ever truly exist? In a physical sense, yes. It was a pattern of neural firing. But in the world of shared reality, it is as if it never was. This paradox touches on the nature of reality and evidence. We live in a world where things are real, if they can be observed, measured, shared. But our inner lives are filled with a universe of experiences that are fundamentally private, a lifetime of unspoken thoughts, unfelt emotions. This inner world is for each of us the most real thing there is. Yet, it is completely invisible to anyone else. It is a gentle reminder that reality is layered. There is the outer world of objects and events, and there is the inner world of consciousness. The vast majority of what happens in that inner world remains a perfect, beautiful secret known only to you. As you lie here, your mind may be filled with a quiet stream of thoughts. They are real. They are yours, and they do not need to be shared to be meaningful. Let us now explore a paradox of sound and silence. This is the tritone paradox. A tritone is a pair of musical notes played one after the other. Some people will hear the notes as rising in pitch, while others will hear the exact same pair of notes as falling in pitch. This is not a matter of musical training. It is a fundamental difference in perception. The paradox is that there is no objective up or down. The perception depends on the listener's linguistic background and even the accent of the language they grew up speaking. The brain learns to interpret ambiguous pitches based on the speech patterns it was exposed to as a child. This paradox is a beautiful illustration of how our experience of the world is shaped by our past in the most subtle ways. Even something as seemingly objective as the pitch of a sound is, in fact, an interpretation. It reminds us that we are not passive receivers of sensory information. We are active creators of our own perceptual reality. We hear the world not just with our ears, but with our entire history, with the memory of every word we have ever heard. Each of us lives in a slightly different sensory world, tuned to the unique music of our own experience. Let us consider a paradox of time and art. This is the paradox of a still photograph. A photograph captures a single frozen instant. And yet, when we look at a powerful photograph, a portrait, a landscape, it can feel as though it contains a vast expanse of time. We can see the years of life in an old person's face. We can feel the long, slow, geological time that shaped a mountain. We can imagine the moments just before and just after the shutter clicked. A single, static image can tell a story that unfolds over decades. How can a timeless object contain so much time? The paradox is resolved in the mind of the observer. The photograph itself is just a pattern of light and shadow. It is our own consciousness, our own knowledge, our own empathy that breathes time back into the image. We are the ones who fill the stillness with story. This is the magic of art. It is a collaboration between the creator and the beholder. The artist provides the frame, the frozen moment, and we, the viewers, provide the flow of time that brings it to life. As you lie here, your eyes are closed, but your mind can still conjure images. And in those quiet internal pictures, you can travel through time all within the perfect stillness of this moment. Let us now return for one last gentle visit to the very edge of physics and a paradox of time's end. This is the Boltzmann brain paradox. If the universe is destined to exist for an almost infinite time, eventually reaching a state of random, chaotic equilibrium, then strange things can happen. Over these immense timescales, it is possible for random quantum fluctuations to spontaneously assemble particles into complex structures. It is statistically possible that a fully formed conscious brain could fluctuate into existence complete with a lifetime of false memories. This is a Boltzmann brain. The paradox is this. In an infinitely old universe, it is statistically far more likely that you are a Boltzmann brain, a momentary random fluctuation, than that you are the product of 13.8 billion years of ordered evolution. Your current experience with all your memories is more likely to be a random arrangement of atoms that just popped into being than the result of a real history. This philosophical puzzle challenges our trust in our own perceptions. Most physicists dismiss it as a sign that our cosmological models are incomplete. A universe that predicts we shouldn't exist in the way we do must have a flaw, but it is a deep and unsettlingly beautiful thought. A final cosmic question mark that asks, how do we know our past is real? The answer is that we don't not with certainty. We can only trust in the coherence of our experience, in the beauty of the story, and in the quiet, steady feeling of our own breath. A rhythm too real to be just a random accident in the void. And so our long, quiet drift through the paradoxes of time comes to a gentle, peaceful close. We have journeyed from the one-way flow of time's arrow to the frozen landscape of the block universe. We have walked through the strange, logical loops of time travel and felt the way time itself can bend and stretch. We have listened to the ghostly whispers of the quantum world, where the past seems to wait for the present to give it meaning. And we have returned finally to the soft, personal paradoxes of our own minds, our memories, and our sense of self. These questions do not have easy answers. They are not problems to be solved before you can rest. They are more like koans gentle riddles meant to quiet the striving mind. They are reminders that the universe and our experience within it is far stranger, more beautiful, and more mysterious than we often imagine. They invite us to let go of our need for certainty and to simply float in the vast, quiet ocean of what we do not know. The beauty of a paradox is not in its solution, but in the space it opens in our minds. A space for wonder, a space for humility, a space for peace. As you lie here now, Let these ideas drift away like clouds in a vast twilight sky. Let go of the grandfather paradox, the twin paradox, the whispers of quantum mechanics. They are just stories, just patterns of words that have floated through your awareness for a little while. They have no weight. They ask nothing of you. All that is left is the simple, direct experience of this moment. The feeling of your body at rest. The gentle weight of the blankets. The soft, quiet darkness behind your closed eyes. The steady, easy rhythm of your breath. This breath is your anchor in time. It is not a paradox. It is a simple, perfect truth. It rises and it falls. It has been with you since the moment you were born, and it will stay with you through the quiet hours of this night. Each breath is a small, gentle wave, carrying you from one moment of stillness to the next. You do not need to think about the past or the future. You do not need to understand the shape of the cosmos. All you need to do is feel this breath. Feel it fill you with calm, and feel it carry away whatever is left of the day. The story of time is vast and endless, but your story for tonight is simple. It is a story of rest, a story of letting go, a story of quiet, peaceful surrender. You have journeyed far tonight through ideas that span billions of years and stretch to the very edge of reality. And now, the journey is over. You have arrived here in this perfect, quiet harbor. There is nothing more to do, nothing more to explore. There is only the stillness, the darkness, and the gentle, silent call of sleep. If you happen to still be awake, you are welcome to stay in this quiet space, or to let the next video continue the journey when you are ready. But if your thoughts are soft and distant, if your body is heavy with peace, then simply let go. There is nothing left to hold on to. Just the gentle, certain knowledge that you are safe, you are at rest, and that the great mysterious river of time is carrying you softly, silently into a deep and dreamless sleep. Good night.